Okay, so today what we're going to talk about is conservation of energy, efficiency, and power. Okay, so if we're doing conservation of energy, basically states nothing can be created nor destroyed. So it either changes into one form or to multiple forms. Okay, so that is the conservation of energy. When we have conservation of energy, we have input energy. When it goes into output energy, most of the time you will have heat that causes those to change. Examples of that are like fossil fuels. What are fossil fuels? What are fossils? Dinosaurs. Yes. And dinosaurs are made into coal, right? That's a fossil fuel. So if you think about coal as a fossil fuel, they could break it down chemically, because what they have to do is they have to take the coal, decomposition it by burning it, right, to apply heat. That coal actually makes a machine that works, that changes into mechanical and then electrical. We used to have a steam plant in Conway. That steam plant would take the coal, burn it through the mechanical turning or turning of a turbine, created energy for Conway. Okay, so that's one example of different types of energy. What's a solar cell? Solar panel. Solar panel, right? You have some, I have some at my house where I have lights that actually, yep, got to take it, and what they do is the sun shines on it. It actually turns it into energy and it produces electricity, right? That's what that does. Wind turbines, windmills, how are they used? So the wind causes it to move, right? So it goes into kinetic. Remember, moving is kinetic. Changes by moving the turbine, which is the mechanical, which produces the electricity that we use. Hydroelectricity, that is like a dam, right? Water goes through the dam. As the water goes through the dam, through gravitational potential energy, it converts to mechanical, and then we can turn it into electrical, right? That's how that works. And in a nuclear plant, they use nuclear fission and fusion, which creates heat, which actually turns something that produces electricity. So basically, all these here are just 1, 2, 3, 4, 5 things that we use that we can convert energy from one form to another. And most of the time, heat is produced. Okay? We've done efficiency before. When did we do efficiency? Yeah, AMA and IMA, right? Talking about mechanical advantage. We're going to do efficiency also when we're talking about work, because that's what we're still talking about. So you have N, which is efficiency. So when you see this symbol, that means efficiency equals the E out divided by the E in, and that's the energy. Okay? So to be able to find out how efficient something is you take the output of it, divided by the input of it, and multiply by 100 to give you the percentage of efficiency. And it says current energy concerns when we're talking about these type of energies here: pollution, depletion, cost, and dependency. A while back, we were very dependent on gasoline to convert gasoline, right? So gasoline is in your motor that goes and it converts to what type of energy? Kinetic. You also have mechanical, which makes the tires move, right? And then they also produce a gas on the way out. So if you took that gasoline, that matter's not destroyed, it's just converted into different things. And that's what the main takeaway is on that. And then power is the rate of energy, depends on the work and the performance of in time. So for that, you're going to do power over energy divided by time, or power with work divided by time. When we're doing that, we're going to be using J over S. Okay? Now, yesterday, we had the same problem. A student lifts a 50-pound ball 4 feet in 5 seconds. How many watts of power did the students lift the ball? Well, before we have to do that, we have to find the work first. And this is what we did yesterday. What we did yesterday is we took our units, because our units were in the wrong part. We changed it from pounds to newtons. We changed it from feet to meters to be able to get our work done as the student lifts this ball. So we came up with 271 joules. But now what it's asking us is, how many watts of power did the students lift the ball? So now what we have to do is we have to take our watts divided by time. Here's our watts. So we took our watts divided by our time, and then we got 54.3 joules over seconds, which equals watts. And that's it. So really, in this section with work, we have just this combination of where we did our work and then we did our power. And we just combined them in. Now you're going to be doing that tomorrow at home under the simulations. The simulations, they're going to give you a data table, and you're going to take those data tables and you're going to calculate the work and the power for each of the scenarios. Do you think you can do that? I don't think it's very hard. Now, those of you that are at home, as you see, you have an assignment. What you'll need to do, and I'm going to take you through that real quick. And ladies, if you want to listen, because this will be your assignment on Thursday, I'm going to share my screen. So yesterday at home, and guys that are here tomorrow, you'll be working on the math part of the simulation of what we're doing here in the class, okay? But the people that are at home, what I want you to do is I want you to go down to activity 1.3.3, which is thermodynamics. And what you're going to do is you're going to go and read through, you're going to look at the PowerPoint that's there, and then you're going to answer the following questions about what thermodynamics is. And so you write it in your ISM book, or you can write it in here, either one, it doesn't matter. You don't have to get this completely done today. I just want you to start on that. So my expectation is just the definitions at the very top today, which you will go to question number 9. And that is it.